Hi, my name is Sam and welcome to another one of my VHDL tutorials. Today we're going to be taking a look at pulse width modulation. So, what is pulse width modulation? Well, simply put, pulse width modulation, or PWM that I'm going to refer to it from here on out, is a modulation technique that is used to encode a message into a pulsing signal. The way that it works is that you have your square waveform, which you can see on the screen, and you define what's called a duty cycle. Now, this duty cycle dictates the period of time that the waveform during one of its periods will be high or low. In the case of the screen's example, we have the duty cycle ascertaining to how long the waveform stays at its high state. So, if we refer to the duty cycle 10% example up the top, what we have is we have a waveform that is spending 10% of its period as a high state and 90% of its period as a low state. This is the same for the 30% example, which has 30% for the high state and 70% for the low state. And you can see this trend through the 50% and 90% examples as well. What this allows us to do outside of encoding messages is perform a form of power control to devices such as motors and, in the case that we're going to be doing for this tutorial, LEDs. So, in a system where we have either a high voltage or a low voltage, which is what we're working with, what we can do is we can generate an average voltage between the low and the high state by producing a PWM. So for example, let's say I use the duty cycle of 50%. In a system that has a low voltage of 0 and a high voltage of 5 volts, my average voltage to my device as per the PWM will be 2.5 volts, half of my high state. In the case of a motor, what this will do is this will drive the motor at a slower state or supply less power to the motor. In the case of an LED, what we can do is we can cause the LED to appear dimmer. Not because we're giving the LED a lower power at any one time, but because if we flash the LED fast enough, it can't be visually perceived that the LED is flashing, so it appears as an average lower brightness. So, with that out of the way, we can begin the code. But before I do, I just need to quickly mention that I have included the unsigned library on top of the standard library, as I know that I will be doing incrementing of standard logic in this design. So if you're going to do that, you need one of the signed, unsigned libraries or the arithmetic library. Okay, so let's, as always, begin with the entity. Entity PWM is, and I'm going to include some generics in this design to make it a little versatile. The first of these generics is going to be what I'm calling max value. Now, max value represents the highest possible count value that our counter in our design can get to. In this case, I'm going to default it to 1000. Now, the reason I choose a number like 1000 is that this value defines the resolution and the frequency of your system. So you need to give some thought to what you want. Do you want something that's extremely high frequency, and are you willing to trade off the resolution for that, or vice versa? In this case, if I do 1000, I have 1000 steps, which visually is much harder to perceive than something like, say, 10 steps, which you will be able to begin perceiving. And I also still have an extremely fast frequency because my system is natively running at 50 megahertz, which means that at 1000, the direct laser is just running at 50 kilohertz, and 50 kilohertz definitely can't be perceived. I think it's generally considered that 60 frames to 90 frames a second is the area that humans can perceive frame rates, and then anything exceeding that tends to be hard to perceive. Though I'm sure there are people that will disagree with that. That is what it is off the top of my head. Next is what I'm going to call val bits. And this is simply the number of bits that we need to express the counter and maximum value. So in this one, I've defined a maximum value of 1000. So the minimum amount of bits I'm going to need is 10, as 10 bits is 1024 total values. We can close the generic and open up a port. And as with all my designs, the port starts with the clock input. We also have something that I'm going to call value current. And what value current is it's the input that defines the duty cycle. So I'm going to put it as a vector, and I'm going to make use of that val bits right here and go val bits -1, which in this case will be 9 down to 0, which makes it default to a 10-bit vector. And as I change this value, it will change the high end of this vector. Now, when defining a value for val current, it's purely dependent on what your max value is. So for example, if I wanted a 50% duty cycle, I would need to set val current as half of max val, in which case is 500. You just need to do a little bit of maths to figure out what val current should be, which is another good reason to choose something like 1000, because this way it's very easy to figure it out. Finally, I need an output, which I'm going to call pulse, and this is going to be my single bit output that's going to be either a 1 or a 0, so it's going to be the waveform coming out. And I can end this entity. Start my architecture arc of PWM, and for this one I only need one signal, and it's my counter, and that counter just needs to be the same size as the max val and the val current, which is val underscore bits -1 down to 0. Very simple. And with that we can begin. So we write begin, literally. I'm just going to add some more spaces before I begin. There we go. So first process, is going to be our counting process. So effectively what increments the counter. I do my rising edge of a clock, dash all over the place at the moment, and clock equals 1. Then now we need to do a check. We need to check our counter against our max value. So is count less than max value? And it's actually max value -1, because even though I've set max values are 1000, 1000 counts in total is 0 to 999. So I need to put that -1 in there just to be accurate. Then count is allowed to increment if this is true. Else, count needs to reset. And we just reset by writing all the bits in it to a 0. And that's it for this process. Very, very simple. The next process is the process that controls whether it's a high or a low, which I'm just going to call pulsing. And clock equals 1. So in this one we need to check value current, and we need to check where value current is against the counter. So I'm going to do value current if it is greater than count, which means that counter has not got in front of it yet. So counter starts at 0 and it keeps counting up, and we're looking for count to pass val current, and then the waveform inverts. Now we have a choice here. We can make it as a initially low PWM or initially high PWM. So in initially low, the duty cycle will refer to the period of time that it's off, and in a initially high system it will refer to the period of time that it's on. In this one I'm going to do, as per the example, it's going to be initially high. So my duty cycle is going to refer to how much time this PWM spends at a high logic state. So if we have val current is greater than count, that means count has not reached it yet. So that's where I want it to be a high logic state. And if it has reached it, it is allowed to go to a low logic state. And that is all we need for this process. And actually all we need for the entire component. So that is very simply your PWM component, and is simply controlled by these two processors. Now, to interact with the board that you see down the bottom right hand corner, we're actually going to work on a test wrapper as well. And for those who aren't aware, the definition of a test wrapper, what a test wrapper is basically a piece of code that we write as like an in-between point between our design and our hardware that allows us to test the design on the particular hardware. Sometimes that's very straightforward, like this case. Sometimes you need to change things around, like compensate for a lack of hardware, so on and so forth. So we're just going to do entity test wrapper is port, and we just need to look at what inputs and outputs we have. So we only really need the clock as the input. And the output, well, I said we're going to do LEDs, so we should probably define some LEDs. And in this case, so it looks better on the camera, I will use all of them. Oop, I don't need that one though. And we can end that entity. So now we can move on to the architecture. So we do architecture, arc of test wrapper is. Now the first signal I'm going to define is one called pulse pass. And the idea of this signal is simply to act as a buffer between the output of my PWM, which I'm going to do as a component, and the output of the LEDs. So I will write the output of the PWM to this, and then this will be fed to each individual pin of the LED vector. So in the end, the output we're getting will be written to all 10 LEDs at the same time. The next signal we're going to do is what I'm going to call clock divider, which, as the name suggests, we're going to do a clock divider with this one. Now, what I want to do with this test wrapper is I want to have the duty cycle varying from 0 to 100 and then back to 0, so we can see the LEDs gradually getting brighter and dimmer. Now, what I'm going to do is I'm going to do it so it takes a second to get from 0 to 100 and then a second to get from 100 to 0. So the entire process will take 2 seconds. If I want to do 1,000 counts in 1 second, I need it to be running at 1 kilohertz, so 1 millisecond per count. Considering that we have a 50 megahertz clock, which means that each clock cycle runs at 20 nanoseconds, there will be 50,000 clock cycles in 1 millisecond. So fairly simple math. So 50,000 cycles. Now for 50,000, the smallest we can represent that in is 16 bits. And I know that because 16 is a very common data size that people should know, that 2 to the power of 16 is 65,536. Finally, what I will need is a signal that is actually passing the current value of the duty cycle, into the component. So I will call it duty cycle. And as we know, the maximum value was 1,000 that we're using for this. So I only need 10 bits for that one. Whoops, 0. And that should be all the signals that we need. So let's begin. Actually, let's not begin just yet because I need to include the component. So when including the component, I'm just going to go back here and look at that, copy all that, paste it in, and wherever it says entity, I'm going to change that to component. Fairly simple. Cool. Now we can begin. So the first thing we're going to do is we're going to write the pulse pass to the LEDs, and I'm going to simply do that as LED is others pulse pass. So all bits of the LED vector get written as whatever pulse pass is. Very simple. Next, we will declare, we will do the instance of the component. So PWM, I will write the generic map just in case. So max vel was 1000. Vel bits was 10. Whoops. Clock map, there it is. Clock goes to clock. I typically like to lay out my port maps line by line. It's much easier to debug later. Vel current we said was going to come from duty cycle. And pulse goes to pulse pass. Pulse pass, there it is. And we can close that. Now, the last thing we need is, as I mentioned earlier, a clock divider and something that's counting from 0 to 1000 and vice versa. So we'll do our clock divider first. So process clock begin if clock dash event and clock equals 1. Oops. Then if count, nope, I didn't call it count, I called it clock divider, that's right, is less than, now I said it was 50,000, however since 0 is our first point that we're counting, oops, it's 49,999, I'll just put an underscore there. You can put an underscore in this and it effectively, it doesn't change the number, it just is a visual representation of a divide like we would do for with a comma. So it's just when you get very large numbers, that can make it very easy to infer how many zeros there are. Now, if we're at less than that, I'm going to increment it. Else, I'm going to write it to 0. Now, we're going to need to expand our design a little bit. Oops, after I write this back to a 0. Because what we're going to want to do is we're going to want to allow us to do this increment. I actually already have the arithmetic library here, but I will change that to unsigned. I was under the impression I didn't have that. I do have it though. I have something that will do it. So, what this will do is, this will do the clock dividing, but we haven't done the duty cycle yet. So, there are two ways we can do this. We can include the duty cycle control in this, or we can have this pass a signal that just pulses and increments the duty cycle, and I think I would rather do that. So, I will add another single bit here called, we'll just call it flag. Simple. Now, what flag's going to do is, if this is still counting, flag is going to be a 0. If this is done counting, flag is going to be a 1. And the way this works is that this will only do this for one clock cycle. So when this if statement becomes untrue, there will be one clock cycle where we enter here and this gets written as 0 and this gets written as 1 at the same time, because this is hardware parallelism we're working in. The very next clock cycle, we're back here. Counting again, flag's back at 0. But it means we have one clock cycle, the flag's at a 1. And we can use that to do a single execution of something. So, let's start a new process. Process clock. And I'll just give this a name too. You can put names in front of process. Oops. You can put names in front of processes. I'm just in the habit of commenting it. It's probably better to put the name in front of it, to be honest. The next one we're going to do is the duty cycle. Cycle, there it is. Okay, so let's start with that flag. If flag is a 1. So we're in a position now where we want to do something with duty cycle for one clock cycle. So this will be up for one clock cycle every 50,000 cycles. The next thing we need to do is we need to actually figure out if we're counting up or we're counting down. Now, since we need something that keeps in mind if we were counting up or counting down, we're going to need a new signal again, which we will call pole. Pole for polarity. Cool. So, what I'm going to do is I'm going to do a check here. If pole equals, flag equals 1, if pole equals 0, so I'm going to do pole 0 as my counting in the positive direction. So, if duty cycle is less than, we'll count in 1 and 999. I'll just leave a 1% on either side just to be safe. Typically, you won't see that very last percent, like you won't be able to see it, you won't be able to perceive it, so it shouldn't matter. Duty cycle is less than 999, sorry, then duty cycle can increment. And pole is still a 0. Otherwise, pole's going to go to a 1. Now, we do an else, so now pole equals 1 if duty cycle is greater than 1. So like I said, I'll just do a 1% error margin on either side. Then duty cycle, is going to decrement. And pole's going to be a 1 there. I'm just going to keep it as 1. Else, pole is a 0. Oops. So just to recap, this here is our 1 millisecond pulse. This is our polarity. And this is just checking the maximum value that we're counting up to while we're at 0, or the minimum value that we're counting down to while we're at 1. That will effectively cycle through the values that we have for PWM. The last thing I'm going to need is to make sure I end the architecture. So, and I've included a end if there instead of an end process, so I apologize for that. Certainly helps if you have the right one. With that in mind, that should be everything that's done, that needs to be done, sorry. So I can save that one as well. I can double check that in my hierarchy I've got test wrapper written as the top level, which I do. So I can now go ahead and compile that. And while I'm compiling that, I'm just going to turn the board on. Oh, and we've got an error. I've just missed a semicolon. That happens. Now, while that is compiling, assuming that it compiles correctly this time, which we'll just see if it does. There it goes. What I'm going to quickly discuss is in Quartus we have what's called the pin planner. Now, the pin planner is a nice little tool for people who are relatively new to this and want to assign pins in a safe manner. So this will basically do it in a way that, you know, if I know that my clock that I'm using is pin M9, so I can just write pin M9. I hit enter and it automatically does it. And that will write it to the file that saves this stuff. And the reason I say it's safe is because if I try and put pin M9 there, it will complain and say, hey, don't do that. You know, it's already assigned. And it will then get rid of it, hopefully. However, if you're a bit more experienced, this tends to get quite tedious and clunky, so it's completely up to you. But what I'm going to show people how to do is to directly access the QSF file. So in your files, if you bring it up and go searching for a new file and change, if you change it over here, I'll just make that so it's visible. You change it over here so that you go to all files in the root directory of your project, you'll find this little guy here called the QSF. And you can add that, which I've already added it, so I won't add it again. And then he'll be over here. And if you double click that, you can directly edit it. Now you'll have a copyright from Altera, just general information. You'll then have project specific variables and assignments, which I would not go changing them at all, as this is the specific device that I'm using, and so on and so forth. And then here is where I wrote my clock. Now, what you can do is, and I tend to do this, is I have a list of the assignments, the default pins for the DE0, and I just tend to write my entities the same for the LEDs and etc. every time. So I can just go copy paste straight from my saved file, and this will automatically do it. So if I just save that, and then I recompile the design, the pins will now be included, so we'll actually have the location of the inputs and outputs in your test wrapper. Every time you change a pin, you have to recompile, because it has to run through the hardware consideration section of the overall compilation. So analysis and synthesis, that was a bit of a tongue tie, will only check syntax. You have to get to the later stages of your design compilation, depending on the IDE that you use, the IDE that you're using. They may not necessarily run the analysis again if they know you haven't changed anything. So that's done. What we can do now, is we can open a program device, and I need to add the file, which we can add it there, and let's upload it. And what we end up with is a visual effect that's slowly going, well, when I say slowly, in the process of a couple of seconds, slowly going from a lower dimness to a higher dimness by effectively changing the value of that duty cycle by 1% every millisecond. Now it can be seen, I'm not sure how well it'll be seen in the camera, it certainly is definitely pretty obvious in person, that the higher end of the duty cycle is harder to perceive. So when you're getting around 60% onwards, that's a rough estimate, it becomes a bit harder to actually perceive the increase in brightness. So when you're doing this yourself, you can typically just play around with what you want as your upper or lower thresholds and get a nice sense of it bouncing evenly on the low end and the high end of the duty cycle. In the end though, approaching it this way does give that nice smooth visual effect. There's no visible steps, not in person again. It's just a nice cycle between the dimness of the LEDs. So in the end, that's a very simple way to do it, and the PWM component itself is very, very easy to do. With that, I'll conclude this tutorial. I hope that this has helped people, and if anyone wants to have a look at the code themselves, and feel free to use it, that's why I do these, please find a description in the link below.